I'm first time here, so please forgive me if I sound a bit nervous. Good morning, everyone. I'm Hilary from Beijing University. I'm very honored to be here presenting our work, Finesse, an Agile design framework for pair-based cryptography via software and hardware co-design. And here's a quick table of contents. First, I'll introduce the motivation and background behind Finesse, and then the framework itself, including its abstraction and design flow, and also evaluations of key research questions. As we all know, as society evolves, security and privacy needs is evidently on the rise. It can be seen from the flourish of the blockchain system and also from the increasing discussion on privacy protection. In this regard, as a key enabler, binary pairings are central to modern cryptographic applications, but they are structurally very complex and computationally expensive, typically 2 to 3 orders of magnitude slower than the classic elliptic curve cryptography. And many acceleration solutions have since been proposed. But there are many challenges to these solutions. The first is that the attacks might be improved, and it reduces the security level of the currently existing curves. And also the computational power is growing, and that, so that more curves may be trackable. We have trackable attacks. And furthermore, more applications are emerging, and all these brings evolving requirements on pairing accelerators. They call for more curves, adaptations, and updated using newest security levels and maybe higher throughput for deployment. Our first motivation is regarding the design cycle. Earlier, architecture designers often build a multi-layered algorithm into nested finite state machines, or manually transcribe these algorithms into microcode. And this process requires heavy human intervention and significant manual effort. And adapting to different curves makes things even more trickier. And this gives us a strong motivation of pursuing agility-based framework. Our second motivation is fast and flexible. From our perspective, prior work falls into 2 types. The first type is flexible designs. They are very good in their own perspective and maybe at that time. But from our perspective, though they have ISAs and compilers, they still suffer from relatively fixed hardware architectures and insufficient optimizations. And as another side of the coin, fast designs also exist. They have very low latency and very high throughput, but they have more fixed architecture and introduce more assumptions on the curve structures. Therefore, it is natural for us to ask, can we propose a design flow that achieves both of them? Can we have both performance and flexibility? Maybe we don't need 100% or overwhelmingly better than before. But if we can achieve maybe like 90% on 2 aspects, it's very attractive for deployment. And our third motivation is regarding co-design. For example, as a well-known algorithm based on divide and conquer, the Karasuba algorithm is normally conceived as an optimization. But under the scope of hardware accelerators, it is not always so. Sometimes it will be better to accepting more multiplication instructions, and by disabling Karasuba in certain levels. And this effect is determined by the complex co-effect in software and hardware. So we need a co-design mechanism to efficiently maybe explore these kind of design options. To sum up, our contributions are first, an agile design framework for PVC hardware accelerators, which brings agility by automating the heavy lifting part. And second, we have an abstraction system that covers the process of pairing computation in full, making a systematic approach. And third, we incorporate co-design mechanisms in our framework to optimize using both software and hardware semantics. And finally, we have evaluations of key aspects of this research. So, what does Finesse framework looks like? I think it can be viewed as a black box toolchain. For example, given a pairing algorithm, a portrait pairing algorithm, and optional constraints and optimization targets, it is able to produce a fully functional hardware accelerator at the RTL level in the form of IP cores. And the artifacts can then be integrated into system on chips or be further tweaked freely. So to support these effect or these framework, we need a methodology based on abstractions. So Finesse is built on 3 abstractions that spans pairing calculation from top to the very bottom. First, we have an intermediate representation that captures pairing semantics. And second, we have a domain-specific ISA which encodes low-level operations. And third, we have a hardware model that defines instruction timing and architectural constraints. And next, I will elaborate on them. In the middle, on the ISA level, we have a risk-flavored ISA on the base field level with very long instruction word extensions, which captures a common basic field as primitives and can be extended to include more specific hardware intrinsics. And on the IR level, we have common operations with both finite fields and elliptic curve operations. For example, we have basic operations like addition, multiplication, and also some adjoining and Frobenius isomorphism. And also the elliptic curve, we have point operations like addition or scalar multiplication, etc. And on the hardware level, we have a hardware model describing the behavior of the hardware implementation. This includes instruction itinerary providing latency info and resource consumptions, and pipeline configurations such as number of linear ALUs or some other structures, and memory structures, for example, bank association and simultaneous read-write capacities, etc. Okay, when we have already formulated the abstraction system, we can build a modular design flow on top of that. We have 3 main blocks that form a co-design loop. The first is compiler, and then hardware implementation, and then the simulator. In contrast to modern general-purpose compilers, Finesse use a shorter compilation pipeline. It includes common SSA optimizations and also customized allocation and scheduling techniques. The key part of the scheduling the compiler passes is our affinity-based scheduling, which uses hardware latency info to define affinity hints and performs local dynamic programming to select compatible operations to achieve a better scheduling of the total algorithm. We also need a hardware implementation supporting our ISA. We have built a highly parameterized design to enrich the design space. It exhibits, for example, the number of cores and the bit width and memory structures and latencies can be parameterized and can be configured at compile time. And the architecture exhibits parallelism on multiple levels. For example, instruction level and single instruction multi-threads and very long instruction words. And as a whole, it can be put into standard EDA tools to generate feedback for co-design, and it can be also evaluated in parts. Next, I think it's better to put it in the whole design loop to visualize the role of the simulator. Our simulator supports the design flow in multiple modes: a fast mode for validation only, and a central accurate mode for high-quality feedback. Back to the search engine. The search engine will decide the configuration that the compiler and hardware needs, and after running them, it sends the artifacts into the simulator. And also the performance information of the hardware implementation is collected using standard EDA flows and also included in the feedback. Next, we have the evaluation part. First, maybe most people will like to focus on is general performance. We have tested on both FPGA and ISCA and gathered results from vendor-specific toolchains. Results have shown that this design achieves maybe 6.2%, 6.2 times ISO error throughput comparing to previous flexible framework, and 3.2 times ISO error throughput comparing to ASIC SOTA. And as of scalability, we want to know if our design scales well with the curve, maybe curve parameters. We have collected synthesis results for 7 curves from 3 families, and our design shows sub-quadratic delay and area growth with respect to bit width, and also a reasonable blow-up relative to security levels. It is worth noting that the security level of the pairing itself is not linear. For example, for the 254 bits of BM pair, we only have maybe 100 bits of security level, and as the 638 version has only maybe 153 bits of security level. So when divided by this value, we want to see it is controlled in a reasonable range, and we do not pursue maybe a near linear relationship like with respect to the data bit widths. And this shows that the design scales well with bit width and security levels. Next, we have compiler, and this is an issues queue snapshot for the 7 curves, and each instruction occupies a single slot in the issue queue. This is taken during the simulated execution of the target code. You can see that our compiler can automatically achieve a better utilization, providing a solid building block in the code design loop. And further details of this is available in the paper. As a co-design, we have examined the effectiveness of co-design and design space exploration under 2 scenarios. For example, Finesse can successfully uncover the relationship between operator variants, optimization variants, and pipeline configurations. And it can determine best combinations of the different architectures. For example, on a limited parallelism architecture, the scoop book multiplication might be better. And on architectures with more parallelism, the full Karasuba approach is near optimal. And Finesse provides a systematic approach to automatically adapt to all of them. And on single dimension, using performance info gathered from EA backend, Finesse can identify the best trade-off between IPC and ARU latencies. For example, more allowed ARU cycles means lower critical path delay, but it will also cut down IPC since it will stretch the data dependency and make it harder for the compiler to schedule. For example, here our framework shows that under single issue architectures, maybe 38 cycles of modular multiplication can achieve best trade-off. And finally, we have agility in practice. Finesse provides practical agility. It compiles in only minutes and support rapid curve migration with co-optimized backend, which brings a productivity boost for researchers from both cryptographic and hardware backgrounds. And here is a layout of example layout of a quad-core accelerator IP design using Finesse, which shows the practicality of the framework. And to conclude, Finesse is an Agile framework for PVC hardware accelerator design, which is powered by a multi-layer abstraction covering current computation in full. And with co-design mechanism, we are able to explore more design options and achieve overall high performance. As a whole, Finesse makes accelerators more accessible by providing agility in the design process. And that's all contents. And thank you so much for your attention.